Welcome to Review Lecture 6-2A, Part 1 of 2 parts of Magnetic Fields Current. Upon finishing this, you should be able to determine the magnetic force on a current-carrying conductor, determine the torque on a wire loop, determine the magnetic field of a current-carrying wire, apply Ampere's law to a long straight wire, determine the magnetic force between parallel conductors, and determine the magnetic fields of solenoids and toroids. Okay, now magnetic fields in atoms are produced by two types of electron motion, but the operative word here is motion. One is electron spin. That's the main contributor to magnetism. A pair of electrons spinning in the same direction will add together and create a stronger magnet. A pair of electrons spinning in the opposite direction will cancel the magnetic fields of each other. And the other way that the electrons produce magnetic fields is the revolution about the nucleus. Neutrons and protons also produce magnetic fields, but these are more than 1,000 times weaker than those produced by electrons and generally not considered to be important. All magnetic fields are produced by the relative motion of moving charges, and we'll talk more about this later. So if you are a Physics 222 student or you have calculus, stay here. If not, then please skip to the next slide. Okay, so the magnetic force on a current-carrying wire. We have a current-carrying wire and a magnetic field. The current's going up the page, the drift speed's going down the page, the magnetic field's coming at you out of the page, and by the right-hand rule, the force on the moving charges in there would be off to the right, and that would also be the force on the wire, too. And if you look at this from the side, here's the current down the length of the wire. Okay, current's going in this direction down the length of the wire. The magnetic field is this way. The angle between the magnetic field and the length vector here, or the angle between the magnetic field and the wire at this point, is phi, and we have a force FB from this particular interaction from the magnetic field and the current in the wire. Okay, so then we say the magnetic force on a moving charge is FB equals QV cross B, or FB equals QVB sine phi. The direction is, of course, determined by the right-hand rule. The current, of course, is just a bunch of charges all moving in the same direction. So the force on all of them equals the force on one charge times the number of charges. The current I is just a charge of 1 times the number of charges that move past a given point at a given time. The charges move with a drift speed Vd in a straight wire of length L and a magnetic field B where phi is the angle between B and L. So Q equals I times T, that equals I times L divided by VD. FB is QVDB sine phi, or ILB sine phi. For a straight wire of length L, this can be written as FB equals IL cross B, where L is the length vector of magnitude L directed along the wire segment in the direction of the conventional current I. For a bent wire or non-uniform field, the differential form is DFB equals IDL cross B, where the direction of the length vector L is, or DL, is in the direction of the current. And of course, that would be the conventional current. Now, for those who do not have calculus, Physics 122 students, magnetic force on a moving charge is FB equals QBB sine phi. The direction, of course, is determined by the right-hand rule. You have here a wire with a conventional current flowing in. Of course, the drift speed on the charges is down the wire. Conventional current is flowing up. Okay, the magnetic field is coming at you out of the page. The force on the charges, the moving charges, is FB, and that's off to the right here. And by the way, that's also the force on the wire that contains the moving charges. If you look at it from this angle here, we have the current going down the wire like here. Okay, here's the current, here's the length of the wire. And the magnetic field is in this direction. The angle between the magnetic field and L is phi, and FB is up here. It ends up being FB equals QVB sine phi. The direction, of course, is determined by the right-hand rule. A current is just a bunch of charges all moving in the same direction. So the force on all of them equals the force on one charge times the number of charges. The current I, of course, is just a charge of 1 times the number of charges that move past a given point at a given time. The charges move with drift speed Vd in a straight wire of length L and magnetic field B, where phi is the angle between B and L. And Q equals I times T, or I times L divided by Vd. FB is just QVDB sine phi, or ILB sine phi. Now, of course, we have a right-hand rule. We have dozens of these. I've been collecting these for years. I keep coming across new ones all the time. Of course, it's called a right-hand rule for a reason, because you're supposed to use your right hand. You point your index finger, which is your current finger, or the charged motion finger, in the direction of current, and of course, this is conventional current. And I for index, I for current. You point your middle finger in the direction of the magnetic field, M for middle. Right, okay, M for your middle finger. Your thumb then points the direction of the force, or thrust, FB. Now this works for positive charges in conventional Ben Franklin current. For negative charges, the force will point in the opposite direction, or you use the patented Carroll-Whistle left-hand rule for negative charges. Okay, now in this example, we're going to try to float a current carrying wire in a magnetic and gravitational field. So we have a straight horizontal length of copper wire has a current I of 28 amps running through it. The linear density, which is the mass per unit length of the wire, is 46.6 grams per meter. What are the magnitude and direction of the minimum magnetic field B needed to suspend the wire, that is to balance the gravitational force on this wire? Okay, so we write down the knowns. The knowns is the current is 28 amps. The mu is 0.0466 grams per meter, and G is 9.8 meters per second squared. Now, of course, notice you convert everything to SI units. And by the way, you should always convert stuff to SI units, because if you don't, your test grades are going to be bad, your homework grades are going to be bad. It's not a good idea to skip the SI unit conversion. The physics of this is Newton's law, magnetic force on a current carrying wire. The formula is a force balance, so summation forces equals 0. So we can say that FB equals ILB sine phi, where phi is, of course, 90 degrees, because we want to have the maximum effect from the minimum magnetic field. And, of course, mu, which is the linear density, that's just m over L. So then we solve for summation forces has to equal FB minus mg has to equal 0. And we can rewrite that as ILB equals mg. We can solve this for B equals mg or IL, or mu times g over I. At this point, we're ready to put our numbers in. So we wind up with 0.0466 kilograms per meter for mu. Our old friend G is 9.8 meters per second squared, and we have a current of 28 amps. The magnetic field required would be 1.6 times 10 to minus 2 Tesla. By contrast, the Earth's magnetic field is about 5 times 10 to minus 5th Tesla. So you couldn't use the Earth's magnetic field to do this. You need a much stronger magnetic field than that. Okay, now we're going to talk about another example, a rail gun. An electromagnetic railgun can be constructed as follows. A conducting bar, a mass M, lies across and slides over two parallel conducting rails separated by a distance d. The bar is perpendicular to the rail. A power source causes the current I to flow through the rails and the bar. A uniform magnetic field B is maintained, and B is perpendicular to the plane that the rails and the bar lie on, so B is directed upward here. If the bar starts from rest, derive an expression for how fast it will be moving after it's covered a distance x. Railguns have been the holy grail of backyard physicists and have been studied as possible ways of getting payloads into orbit or to cause nuclear fusion through high-speed collision. The U.S. Navy is also developing them for ordnance on ships. Okay, so you write down the knowns. You know that V naught equals 0 is going to start from rest. We need Newton's third law, magnetic force on a current carrying wire. And we're going to assume the friction is negligible, so the acceleration is constant. And it would be made this way if at all possible, because nobody wants friction. So formula, summation F equals MA. F equals IDB sine theta, or IDB. Of course, we want the sine theta be 1 to get the maximum effect. That also equals MA. So IDB equals MA. We have a kinematics equation, V squared plus V naught squared equals 2AX. And we can get rid of the V naught because it's starting from rest. So V squared equals BIXD times 2 divided by M. We solve this for V. V is the square root of X times B times I times D times 2 divided by M. We want to make V as big as possible. So we need to maximize everything on the top here. So we need to B, I, D, and X to all be maximum. And we want this mass to be as small as possible. Now, these goals actually require balancing D and M to achieve the lightest mass and the longest length D, while still retaining the strength necessary to resist the tremendous stresses of launching. There would also be a necessity of keeping the thickness of the launcher bar high enough so the electrical resistance is low. Because it's going to take a fair amount of current to do this, and you don't want to melt your bar here and have it stick to the rails. And I've seen a video of one of these, a test on one of these types of things. These things really get up to speed. And the speed was so high that basically the projectile was like a meteor. It was on fire from the friction in the air. If I can find that video, I'll post it. Okay, a rectangular current loop is in a uniform magnetic field. The current of the loop is counterclockwise. What is the direction of net force on the loop? Well, you're going to use the right-hand rule on this. If you do that, you find that each of the 4 wire segments will experience a force outward from the center of the loop. Thus, the forces of the opposing elements cancel, so the net force is 0. So here we go. We're going counterclockwise around this loop, and I started here on the left-hand side. So I take my index finger, point it into the page. Magnetic finger, which is middle finger, points up. The force is out. If I go to the back thing here, The magnetic finger is still pointing up. The index finger is now pointing to the left in the direction of the current, and the force is still outward, away from the center of the loop. If I go to this one, I wind up with the index finger pointing out of the page, the magnetic finger pointing up, and the force finger, the thumb, pointing away from the center of the loop. If I go to this, I'll wind up with the same thing. The index finger is going to the right, magnetic finger is going up, and the force finger, which is the thumb, is pointing outward. So all of these forces cancel to zero. But the torque does not cancel to zero necessarily. Okay, so we have a current in this loop here as shown, and it's in place between the ends of a horseshoe magnet. Okay, so what's going to happen to the loop? Well, you want to use the right-hand rule on this. Okay, if we look at the North Pole, the magnetic field is pointing to the right and the current points out of the page. So your index finger is going to be pointing out of the page and your middle finger is going to be pointing to the right. Your thumb points up. So this side of the wire will experience an upward force on it. And if we do this on the other side, your index finger is pointing into the page, your magnetic finger is pointing to the right, still toward the South Pole, and your thumb is going down. So this is going to rotate clockwise. Okay, so if you bend the wire in the loop, okay, you can end up with a torque on a current loop. The net force on the loop is the vector sum of the forces acting on its four sides and cancels to zero. But the torques do not completely cancel. The net torque acting on the coil has a magnitude given by tau equals NIAB sine theta, where N is the number of turns in the coil, A is the area of each turn, I is the current in the coil, B is the field magnitude, and theta is the angle between the magnetic field B and the normal of the coil N. And you can see this right here. Here, of course, it's shown this way. And here are the two forces, just like we did in the previous problem. Here we turn the loop a little bit this way. And you can see we have a force up here and force down there. That will have a tendency to make this whole loop rotate clockwise until this normal here, which is always perpendicular to the face of the loop, aligns with the magnetic field. At that point, the torque disappears. Remember, the angle is always measured relative to the normal. So the normal is perpendicular to the plane of the coil, and a memory aid is angles are normally measured relative to the normal. The actual shape of the loop does not matter, only the area matters. A loop that is free to rotate will turn until its normal N aligns with the magnetic field B. So a memory aid for this is a current carrying loop or coil tends to align to enclose the maximum number of magnetic field lines. And this is the basis of the electric motor. So what's actually going on in here is a current carrying coil will generate its own magnetic field and thus behaves like a bar magnet when it's placed in a magnetic field. So we can assign a magnetic dipole moment mu to account for this torque due to the magnetic field. So here we have a coil, and when you turn on the current, it creates its own magnetic field. The direction of the moment is the same as the normal vector of the plane of the coil and follows the following right-hand rule. Coil the fingers of your right hand in the direction of the current around the coil. Your thumb will point in the direction of the magnetic dipole moment mu. Okay, so we've cut this coil in half, and we're looking down on the lower half of it. You will put your hand palm up, so your fingers are pointing at you in the direction of this current that's coming at you out of the page. Your thumb would point along this direction of mu, along in this green line here. Now the forces here are going to cause a torque that will have a tendency to rotate this coil until this green line lines up with the magnetic field lines, which are these lines going off to the right here. Now the magnitude is given by mu equals N times I times A. And of course, A is the area of the coil, I is the current running through it, and N is the number of turns. So a coil of area A and N turns carrying current I in a uniform magnetic field B will experience a torque tau given by tau equals mu cross B if you are physics 222 or calculus based, which can also be written as, for the non-calculus based physics to 122 students, tau equals mu B sine theta. Theta, of course, is the angle between mu and B, and tau is always perpendicular to both mu and B. Now, this is the basis of an electric motor. I'm not sure if this will work or not. Last time I had some trouble getting this to the sound didn't work real well, but I'll try really hard to make sure it works. Now, electric motors have a rotating coil and magnetic field. By varying the direction of the current in the coil, the torque on the coil can be controlled to keep the coil turning. This simple device converts electrical energy into mechanical energy and has actually revolutionized human society. So think of how many different motors you have in your life and how important they are. Unfortunately, the sound did not come out okay on this, So I'm going to have to post this in the same folder with this video and with the lecture. Okay, this principle is used to both make motors and galvanometers work. The magnetic dipole effect is used to make motors turn. A motor is a freely rotating current-carrying loop placed in a magnetic field. Actually, real motors use multiple coils both to produce more torque and to smooth out the motion and produce a more constant torque. In DC motors, a commutator reverses the current in the coils so the armature or rotor, which carries the coils, will keep on rotating in the same direction. Brushes make electrical contact between the coil and the voltage source. Another application of coils is in galvanometers, which are used to measure very small currents. Okay, now magnetic dipole energy. The orientation energy of a magnetic dipole in a magnetic field is, for calculus-based Physics 222 students, U of theta equals minus mu dot B. This can be written for Physics 122 students or for anybody of U of theta equals minus mu B cosine theta. So the minimum energy is, of course, when theta equals 0 degrees, and that is minus mu B. And that is this situation. That is when mu lines up with B. Now, the dipole will try to align itself in this configuration so that its mu lines up with the magnetic field in the minimum energy position. The maximum energy is the opposite direction, is when mu and B are anti-parallel to each other, and theta equals 180 degrees. And the maximum energy is plus mu times B. If an external agent rotates a magnetic dipole from an initial orientation of theta I to some other orientation theta F, and the dipole is stationary both initially and finally, the work done on the dipole is WA equals delta U, or UF minus UI. Don't forget it's always final minus initial. Now, we've been kind of putting the horse before the cart. A charge can experience a force when it's moving in a magnetic field, but actually it's because the moving charge produces its own magnetic field. This magnetic field interacts with the external magnetic field, and that interaction produces the force, just as two magnets can exert forces on each other through their magnetic fields. An electric current passing through a conductor produces a magnetic field because it has many charges in motion. If you bend that wire into a loop or a coil of many loops, you multiply that field. A current-carrying coil of wire is an electromagnet. Now, you can build your own electromagnet at home, but be very careful when you do this. Okay, because I did one of these one time when I was a kid. I found a big, heavy nail in the basement, and I found some wire that had some nice insulation on it, nice long length of wire, and it was used for making transformers, a transformer wire. And so I very carefully wrapped the nail up in several layers of wire, and I couldn't find a battery. Couldn't find a battery that wasn't dead. So my eye lit on the wall outlet, and I shoved the two ends into the wall outlet. Next thing I knew, there was a bright flash. I was sitting on the floor, and I could hear my mom yelling from the upstairs in the kitchen. She yelled, "Carol, what are you doing down in the basement? All the lights in the kitchen have gone out." I immediately scrambled to my feet, put out the fire, and said, "Mom, it's okay." So this is what happens when you grow up in an electrical engineering family where experimentation is encouraged. I'm surprised that we didn't lose our house. I'm so surprised. Okay, now we can determine the magnetic field of a current-carrying wire. The magnetic field surrounding a current-carrying wire, conductor, or wire can be shown by arranging magnetic compasses or sprinkling iron filings around the wire. When the current is off, the compass needles just line up with the Earth's magnetic field. When you turn on the wire, they rotate until they look like this. So they all kind of line up in concentric circles. And the iron filings will do the same thing. So they produce a pattern of concentric circles around the wire. If you reverse the current, all these will flip around, okay, showing the direction the magnetic field reverses also, because these actually follow, the compass needles follows the magnetic field line. And when the current is turned off, the compasses no longer orient themselves in concentric circles around the wire. So they go back to this. This shows that the current is producing a magnetic field, and it is concentric circles around the wire. So here's some pictures here. This one is iron filings sprinkled on a paper revealing the magnetic field configurations. Of course, this is through a current carrying wire, and you can see these circles. Here is when you bend the wire into a loop, and look how concentrated the magnetic field is, especially between the loop. Then we put multiple loops together, and you can see it's getting more and more concentrated, and it's fairly uniform down the central axis of this loop, and a little weaker on the outside. And this, by the way, is a solenoid or coil, and we'll talk more about that later. So here's the current carrying wire, and if we bend that wire into a loop, okay, look how the magnetic field lines become bunched up inside the loop. And you know what happens when field lines become bunched up? That means the field is stronger. So, and if we add another loop here, the concentration of magnetic field lines inside the double loop is twice that of the single loop. By superposition, the magnetic field intensity increases as the number of loops is increased, and the coil becomes an electromagnet as soon as the current is turned on. And the magnetic field inside the coil can be increased further by putting certain ferromagnetic materials inside the coil. Okay, a wire carrying a current generates its own magnetic field and thus responds to external fields, as is shown by the following experiment. You put a wire between the poles of a horseshoe magnet and turn on the current. The wire will deflect in one direction, up, in this case. If the direction of the current of the wire is reversed, then the deflecting force will act in the opposite direction and the wire will deflect down. The force is a maximum when the current is perpendicular to the magnetic field lines. The direction of the force is along neither the magnetic field lines nor the direction of the current. The force is perpendicular to both the field lines and the current, and it is always a sideways force. So here, this is for calculus-based students. If you're not a calculus-based student, go ahead to slide number 27, or you can stay here if you've had calculus or you're just curious. Okay, so here we have an arbitrarily shaped wire. We have a current running along the wire. We have a small element ds in the wire. We have a point P over here, a distance r from the wire. We want to determine the magnetic field at this point. And of course, we have an angle here, theta, between the wire, okay, the current in the wire, and of course, r. So the magnitude of the field dB produced at point P at a distance r by a current length element ds turns out to be dB equals mu naught over 4 pi times I ds sine theta over r squared. Theta is the angle between the directions of ds and r, and of course r hat is of course the unit vector that points from ds toward p. Symbol mu naught is a constant called the permittivity constant. It's a lot like epsilon naught, whose value is defined to be exactly 4 pi times 10 to the minus 7 Tesla meter per amp, or approximately 1.26 times 10 to the minus 6 Tesla meter per amp. And you should write this stuff down in your notes. The direction of dB, as shown, is being into the page, and you can get that from the right-hand rule. Grab the wire with your thumb pointing in the direction of the current, and you extend your fingers off toward point P and notice that they're pointing into the page. So dB is into the page. So the direction of dB shown as being into the page is that of the cross product ds cross r. We can therefore write the previous equation containing dB in vector form as dB equals mu naught over 4 pi times I times ds cross r divided by r squared. Now for a long straight wire carrying current I, the Biot-Savart law defines the magnitude of the magnetic field at a perpendicular distance r from the wire, and B equals mu naught I over 2 pi r. Or we can rewrite that as B equals mu naught I over 2 pi r times L cross r. The direction of B is given by right-hand rule, which I just said a minute ago, but I'm going to repeat. Grab the wire with your thumb pointing in the direction of the conventional current. The curl of your fingers gives the direction of B. This also works for a magnetic field generated by a single moving charge because the current is just a bunch of charges all moving in the same direction. Now, in this case right here, the current is going into the page. That's the conventional current. Your thumb is going to be pointing into the page, and note that your fingers point clockwise. If it is a negative charge, okay, and you want to have the same equivalent thing, a negative charge wouldn't, instead of being going into the page, would be coming out of the page. And I use the Carroll Whistle patented left-hand rule. Your thumb is coming out of the page, okay, and you're still grabbing the wire or the direction of the charge motion with your hand. Note that your fingers are still going clockwise around this. So it forms concentric circles around. Now, if you reverse the current, this direction would reverse. So in other words, it would be going counterclockwise if the current was coming out of the page. Okay, for Physics 122 students, or non-calculus-based students, For a long straight wire carrying current I, the Biot-Savart law and calculus defines the magnitude of the magnetic field at a perpendicular distance r from the wire as B equals mu naught I divided by 2 pi r. Direction of B is given by a right-hand rule. You grab the wire with your thumb pointing in the direction of the conventional current. The curl of your fingers gives the direction of B. This also works to the magnetic field generated by a single moving charge. So in this case, the current is going into the page. You would grab the wire with your hand with the direction of your thumb pointing into the page. The curl of your fingers around the wire is clockwise. If instead you were considering the motion of a negative charge, that negative charge motion is opposite the conventional current, that would be coming out of the page. If you use the Carroll-Whistle patented left-hand rule, your thumb is pointing out of the page, your fingers are still pointing clockwise. Now, if the current or the charged motion was reversed, the magnetic field would also reverse and would be counterclockwise. Calculus-based physics 222 students, here. If you are not calculus-based, please go to the next slide. Okay, so here we have a straight wire here with a current I flowing up the page. And we have a distance P, okay, we have a point P, a point P, a distance big R from the wire, or a distance little r from this element ds. And of course, the angle between ds and this r here, okay, is theta. And we're going to try to find the magnetic field at point P. So, and this will be into the page by the right-hand rule. You grab the wire with your thumb pointing up the page, and your fingers at point P point into the page, so the magnetic field is pointing into the page. So we wanted to determine the elemental magnetic field dB at point P by elemental wire element ds, or segment ds, excuse me. dB is then mu naught over 4 pi times I ds sine theta over r squared, where theta, of course, is this angle between ds and r. And then, of course, we want to integrate this for an infinite wire length, and that'll just be the integral from minus infinity to infinity of dB. But we really don't want to do that. We can simplify that a little bit by only taking the integral from 0 to infinity and multiplying by 2. So B then becomes 2 times the integral from 0 to infinity of dB. We do some substituting and we pull the constant out. So B equals mu naught I over 2 pi times the integral from 0 to infinity of big R ds over the 3/2 power of the quantity s squared plus big R squared. And we're going to integrate and evaluate between the limits of 0 to infinity. And when we do that, we end up with B equals mu naught I over 2 pi r times this quantity s over the square root of s squared plus r squared, evaluated between 0 and infinity. When we do that, we end up with B equals mu naught I over 2 pi r, where r is the distance of point P from the wire itself, mu naught is a constant, I is the current in the wire, and of course B is the magnetic field. Okay, now you can also bend a wire into an arc, which is part of a loop. It can be shown by calculus, Physics 222, that the magnitude of the magnetic field at the center of a circular arc, a radius r, and central angle phi in radians, be careful, carrying current I as B equals mu naught I phi divided by 4 pi r. Now, if the arc is a single loop, that is phi is 2 pi, that's of course is all the way around, the magnetic field at the center of the loop is B equals mu naught I over 2r. And if you have n loops, a coil, B is just n times one of them, so B is n mu naught I over 2r. Now, the right-hand rule for this, you grab the arc, okay, with your thumb pointing in the direction of the current and your fingers as close to the center of the arc as possible. In this case, you're going to see here, okay, your fingers are going to be pointing out of the page towards you. So in this case, the magnetic field due to this arc is coming at you out of the page. Okay, now here's the derivation of the previous slide for Physics 222 students. If you're an algebra-based 122 student, please skip to the next slide. Here we have an elemental magnetic field dB at point C by elemental wire segment ds. So here's our ds. Here's the point that we're interested in to determine the magnetic field at. And of course, this angle is 90 degrees between ds and r, and here's the distance r. So dB equals mu naught over 4 pi times I ds sine theta over r squared. And theta, of course, is this angle right here. And of course, theta is 90 degrees, so the sine theta is going to be 1. So dB is going to be mu naught over 4 pi times I ds sine 90 degrees divided by big R squared. Now, big R, of course, is this radius here. Okay, so then we can integrate between 0 and phi. So we end up with b equals mu naught I over 4 pi times the integral between 0 and phi of r, big R d phi over big R squared. And we do the integration, we wind up with b equals mu naught I over 4 pi times big R times the phi taken from 0 to phi. And that just becomes b equals mu naught I phi over 4 pi r. Again, the right-hand rule on this is you grab the wire arc with your fingers pointing close to the center, your thumb pointing along the direction of the current in the wire. And the direction of the fingers, in this case, is pointing at you out of the page, and that's the direction of the magnetic field in the arc. Okay, now parallel wires carrying currents in the same direction attract each other, whereas parallel wires carrying currents in the opposite direction repel. Memory aid for this is like directions attract, unlikes repel. Now be careful, this is different from the normal thing like charges. Yeah, it's different from that, so be careful with that. The magnitude of the force on a length L of either wire is FBA equals IBL times BA times the sine of 90 degrees. And we can rewrite that as mu naught times L times IA, IB, divided by 2 pi D. Now D is the separation between the two wires. IA and IB are the currents in each of the wires. If the two currents are anti-parallel, that is in opposite directions, the two wires would repel. Now, this is for Physics 222 students, not for Physics 122. If you are a non-calculus-based student, please go to the next slide. If you're calculus-based or you're curious, stay here. Now, Ampere's law is a lot like Gauss's law. So Ampere's law states that the integral of B dot ds is mu naught I enclosed. The line integral here, that's what this little loop, this little circle in here reminds you that it goes all the way around the loop. Okay, the line integral in this equation is evaluated around any closed loop called an Amperian loop. The current I on the right-hand side is the net current encircled by the loop. Only the enclosed currents count. The ones outside the loop, and of course you can define the loop any way you want, just as like you did with Gauss's law. The ones outside the loop don't count. A right-hand rule for the Ampere's law is used to determine the signs for the currents encircled by an Amperian loop. Now, not only can you decide which currents you're going to include, but you can also decide which direction you want to go around the loop when you integrate. So in this case, you're going to, if we decided here, we have 3 currents here, we're going to enclose these 2 and ignore that one. So we put our Amperian loop around these 2 currents here, and we decided to go counterclockwise. And in this case, you're going to curl your fingers, your right hand, around the loop counterclockwise. And that's just because the direction we chose was counterclockwise. Your thumb will point in the direction for positive current. So I1 is positive and I2 is negative. If instead you decided to go the opposite way, okay, you would curl your fingers clockwise around the loop, and then the direction of thumb would be in the page. So this one would be positive and that one would be negative. Okay, so Physics 122 or non-calculus based students, Ampere's law states that mu naught I enclosed is the sum of B parallel delta L all the way around the loop. This is the line integral or the summation. This to remind you to go all the way around the loop. And this equation is evaluated around any closed loop that's called an Amperian loop. The current I on the right-hand side is the net current encircled by the loop. Only the enclosed currents count. The ones outside the loop, which you are free to define any way you want, do not count, no matter how large they are. And this is like Gauss's law. Remember, only the enclosed charges count? A right-hand rule for Ampere's law is used to determine the signs for currents enclosed by an Amperian loop. You curl the fingers of your right hand around the loop in the direction you have chosen to sum, and you're free to choose the enclosed currents or the direction you choose to sum. Your thumb will point in the direction for the positive current. So here we have 3 currents, and we've decided to enclose I1 and I2 in an Amperian loop. That means we don't have to worry about I3 at all. Okay, so we decided to go counterclockwise. So you take your fingers of your right hand, okay, curl them and put them in the direction, curl them counterclockwise in the direction of this choice here. And notice that your thumb points out of the page. That is positive, for I1 is positive and I2 is negative. If instead you decided to go clockwise around, turn your hands so your thumb is pointing into the page, your fingers curl along the clockwise direction around the loop. And now the positive is into the page, so I2 is positive and I1 is negative. And you sum all the way around the loop. We'll show you an example in a minute. Okay, calculus-based physics 222 students here. Non-calculus-based students, please skip one more slide. We're going to use Ampere's law to calculate the magnetic field outside a long, straight, current-carrying wire. Okay, so the magnetic field has a cylindrical symmetry about the wire, so we're going to pick an Amperian loop that will take advantage of that. And that is one that is centered on the wire. By the right-hand rule, we would integrate counterclockwise, and we want the enclosed current in this loop to be positive I. So in other words, your thumb is going to be coming along the direction of the current out of the page toward you. So your fingers will curl counterclockwise. That will give you the direction of the integration around the loop. We use Ampere's law and integrate counterclockwise. The integral of b dot ds equals b cosine theta ds. And of course, b is constant by symmetry and by experimental measurement on the circle. And of course, b and ds are lying along each other. So we can pull the b outside the integral. So b times the integral of ds is just b times 2 pi r. That is just the circumference of the circle. And that has to equal mu naught I. So b equals mu naught I over 2 pi r. For the non-calculus-based student, the magnetic field has a cylindrical symmetry about the wire, so they're going to pick an Amperian loop that is centered on the wire. Okay, by the right-hand rule, we would sum counterclockwise, so the enclosed current in this loop is positive I. We want the current to be positive I. So we want our thumb coming in the direction of the current, which is coming at us out of the page. Our fingers will curl counterclockwise. That gives us the direction of the summation around the loop. Now we're going to say the summation around the loop of B parallel delta L equals mu naught I enclosed. B is constant by symmetry and by experimental measurement on the circle. And B parallel just lies along the circle. So B parallel times the sum of delta L equals mu naught I. And of course, the sum of delta L around this entire circle is just the circumference of the circle. So we wind up with B naught times 2 pi r equals mu naught I. So we can solve that. B naught equals mu naught I over 2 pi r. This is the end of part 1 of review lecture 6-2. So please go to the second part, which is review lecture 6.2b. Thank you.